Welcome everyone to this explainer. Today we're diving into a topic that is just incredibly cool: shape memory heat engines, from Earth to space. We're embarking on this really fascinating journey, looking at a piece of technology that bridges the tiny, microscopic world of material science all the way up to the vast, infinite expanse of outer space. We're talking about engines that literally transform raw thermal energy directly into mechanical motion.
So I want you to imagine something for a second. What if an engine could run purely on sunlight and the extreme cold vacuum of space, without a single battery on board? Literally no heavy lithium-ion packs to lug around, no complex electrical solar cells that degrade over time, just natural, raw temperature differences powering continuous motion. Sounds totally like science fiction, right? Well, it's actually grounded in some incredibly elegant science.
Okay, let's dive into this. Here's our roadmap for today. First, the wondrous shape memory alloy. Second, early water-driven heat engines. Third, efficiency challenges on Earth. Fourth, a new solution for space. And finally, number 5, a sunlight-driven future. Starting right off with Section 1, the wondrous shape memory alloy.
To really get how this engine works, we have to meet the star of the show, the shape memory alloy, or SMA. You can really just think of an SMA as a kind of thermal muscle. Just like your actual biological muscles flex and contract to move your bones, this unique smart material actually recovers its original preset shape the second it's heated up. And it does this even if you've completely bent it out of shape, stretched it, or severely deformed it while it was cold. It effectively remembers its shape. The most popular version of this is called nitinol, which is a mix of nickel and titanium. So how does it actually remember? Well, it all comes down to a thermodynamics phase shift at the microscopic level. When the alloy is cold, it sits in what we call the martensite phase. In this state, it's highly malleable, super easy to bend, but when you hit it with heat, it forcefully transitions into the austenite phase. Its internal crystal lattice geometrically snaps back to its original preset shape. This forceful, snappy shift is the secret sauce here. It converts thermal energy directly into mechanical motion.
Moving on to Section 2, early water-driven heat engines. Now, what's really interesting about this is how early engineers tried to harness that thermal muscle on Earth. They built these twin-crank SMA heat engines. They basically used SMA helical springs to connect two mechanical cranks. And to force that phase shift we just talked about, they relied on alternating temperatures using a hot water bath. The springs would dip down into the hot water, contract really tightly, and then cycle up through the ambient air to cool down, relax, and extend again.
And here's a similar concept: the offset crank engine. The SMA springs contract the precise moment they hit the hot water at the bottom of the bath. Because the cranks are purposefully offset from the main wheel's central axis, this sudden, forceful contraction pulls the offset cranks closer, which forces the entire wheel to spin continuously. It is just brilliant in its mechanical simplicity. But as researchers really started testing these prototypes, they hit a massive roadblock. Which brings us to Section 3, efficiency challenges on Earth. So the crucial point is this staggeringly low number right here, 2 to 3%. Yep, despite that incredibly elegant mechanical design, numerical simulations, and actual real-world testing confirmed that this was the absolute maximum thermal efficiency of early SMA heat engines. Depending on how big they built them, they were maxing out at just a few measly watts of output power. And the data revealed some really frustrating paradoxes for the engineers. Let's say you try to push the engine to rotate faster to get more power out of it. Well, the output torque actually drops and your overall heat efficiency plummets. What if you shorten the SMA spring? Well, that seemed to help efficiency at super low speeds, but it made performance significantly worse at high speeds. It was basically a catch-22. The core issue was that the natural cooling process in normal room temperature air just couldn't happen fast enough to keep up with the rapid heating happening in the hot water. But honestly, the absolute biggest flaw of all was the heat source itself. Maintaining a giant bath of hot water or constantly pumping hot fluids around an engine is massively energy-consuming. Heating huge amounts of liquid on Earth takes way more energy than the tiny mechanical output the engine actually gives back to you. This inherently flawed energy loop pretty much killed any commercial application. It was, sadly, an engineering dead end on Earth. But what if the problem wasn't the engine itself, but the planet it was sitting on? Let's jump to Section 4, a new solution for space. Let's contrast these two environments for a second, because this is where it gets exciting.
On Earth, we have to artificially heat up water and usually force air with bulky fans just to cool the engine's springs back down. Wildly inefficient. But space? Outer space perfectly and naturally solves every single one of this engine's temperature challenges. It gives us direct, incredibly abundant solar energy for intense heating, and the extreme freezing cold of deep space radiation for rapid natural cooling.
I absolutely love this quote from researchers Gao and Huang. The proposed motor can be driven by sunlight directly without any electrical power. No solar cell is required. Think about that. By moving to the space environment, we completely bypass the need for heavy, expensive onboard batteries that inevitably degrade over time, and we skip traditional solar cells entirely. This isn't just theoretical math on a chalkboard either. Let's look at Section 5, a sunlight-driven future. And this brilliantly illustrates exactly what we're talking about. This is the actual 5-beam offset crank SMA heat engine prototype built by researchers Tang and Huang. It was specifically designed to run solely on concentrated sunlight. Just look at that beautiful, clean design. There are no water baths, no bulky batteries, no complex wiring to short out. It's just pure mechanical ingenuity ready to soak up the sun. Let me walk you through exactly how elegantly this thing operates. Step 1, you have these transparent optical lenses. Those clear blocks sitting on the arms, and they concentrate direct sunlight right onto flat nitinol SMA ribbons. Step 2, those intensely heated ribbons hit their austenite phase, contract forcefully, and boom, you've got driving torque. But step 3 is where the real design magic is. They use a simple cardboard shield to cast a shadow over half the engine. So when a ribbon rotates into that shadow, it cools rapidly via radiation, relaxing back into its cold martensite phase, totally ready for the next cycle. And you know what? The results were highly promising. In initial outdoor tests, just under standard sunlight with no external load, the prototype ticked along at a steady 2 RPM. But the researchers realized, hey, if we optimize this shaded area to cover about 2/3 of the engine, giving those ribbons more time in the cold zone to fully relax, we can massively reduce the internal resistance torque. And with just those smart optimizations to the cooling process, they boosted the speed from 2 all the way up to 9 RPM. Let's move to and see how this builds a really solid case for practical, future space missions. Because this engine operates so smoothly without any electrical shocks or sudden violent mechanical jolts, it is absolutely perfect for driving mechanisms in deployable space structures. Think about slowly, safely unfurling a delicate satellite antenna without snapping it. It could operate thermal shields to protect super-sensitive infrared cameras. It could even be used as a battery-free dust cleaner for rovers on Mars, just running and endlessly and reliably, day after day, as long as the sun is shining.
It is truly incredible, isn't it? How a simple phase shift in a tiny piece of metal alloy, triggered just by the heat of the sun, can unlock such massive potential for deep space exploration. It really leaves us with this final provocative thought. As we venture further and further into the cosmos, leaving Earth behind, could the absolute simplest mechanical muscles actually end up outlasting our most advanced, expensive batteries? Thank you so much for watching this explainer, and as always, stay curious.